word that keeps popping up everywhere these days. So what does it mean? It's a prefix that means really, 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 really small, like smaller than you can ever imagine. So to put nano into practice, we have two different types of sand here, regular sand and magic sand. They're basically the exact same. The only difference is each individual grain of this magic sand has been coated with a layer that's about 1 to 2 nanometers thick. And that nano layer on the magic sand makes it behave differently than the regular sand, and they interact differently with water. So let's move over here to this model. This side represents regular sand. And this side is the same sand coated with a layer that's about 1 nanometer thick. These represent water molecules. Now, when we're talking about water, it's important to remember that water is polar, which means it has positive and negative charges that draw the individual water molecules together. They like each other and form strong bonds with each other. So what happens when you throw regular water molecules onto regular sand? It sticks. Now, what happens when you throw regular water molecules onto magic sand? It falls away. So what's happening is with this regular sand, the surface of these individual grains is also polar, which means it draws the water to it. And now with this magic sand, the coating makes it nonpolar, which means it pushes the water away so that it doesn't stick. So let's move back on over to the sand and put this model into practice with an activity. So what we have here are two cylinders with equal amount of water. And here we have equal amounts of sand, one with regular sand, the other with magic sand. Now if I could get a volunteer to pour the regular sand into one Erlenmeyer flask and the magic sand into the other one. And now we'll pour the equal amounts of water into the flasks. Now, as we pick the flasks up and swish them around kind of gently, then we can notice how the water interacts with the different kinds of sand. So when we swish the sand around gently, we notice that this sand absorbs the water. So with this sand, when we swish it around, we notice the sand doesn't absorb the water. It's floating around on top of it or around it, and the sand is pushing the water away. Now, we started out with the exact same amount of water. What we're going to see is if we can get the same amount of water back into these individual cylinders. Now we're going to do the same with the magic sand. Notice that almost no water got back into the cylinder from the regular sand. It's all trapped inside of the sand. Now, notice that almost all of the water got back into the cylinder from the magic sand. The sand was pushing the water away. Now, knowing all of that, and knowing that this sand was just in this flask with a bunch of water, should this sand be wet or dry? We notice that as it slides down, it's completely dry. Now, one way that this is used in the real world is through cleaning up oil spills. What happens is when oil gets on water, then the water pushes the oil away because the oil is nonpolar like the sand. So if you put huge, massive amounts of the sand on top of the oil, then it becomes so heavy that the oil and the sand sink to the bottom of the water, and then the workers can dredge it out of the water and clean the oil-contaminated water. One other application is for utility companies in cold, cold climates where the ground freezes over. They'll put wires in these electrical junction boxes and bury them underground. But in the winter months when the ground is frozen, it's so hard and labor-intensive to get to these wires to make repairs. So what they can do is put a layer of this magic sand on top of the junction box. Then when it rains and the water seeps into the ground, the sand swishes it away from the junction box, making it easier to get to the box and repair the wires than if the ground was frozen around it.